6 in the textbook, or chapter 2 in the notes. All right. Now, those of you who have taken 560 will recognize this topic, but we'll do it from a bit more theoretical point of view here. So, am I recording? Yes, I'm recording. Okay. So the problem to solve is you're given n plus 1 points in the plane that I'll label by x0, y0, x1, y1, and so forth, all the way to xn, yn. And the only condition on these points is, at least for now, all the x's have to be distinct. Okay, so this has to be a set of points that could come from the graph of a valid function. I'm going to find a polynomial that I'll label p sub n of x. Of degree up to n. That fits these points exactly. So if I plug in any of the x values into this polynomial, I will get the corresponding y value. Okay. Okay. All right, so this is the condition to satisfy. And Pn is the called the interpolating polynomial for all these points. Okay. Now, what we could do is discuss how you might solve this problem in the most straightforward way possible. And that is, so if I were to write this polynomial in its usual form, there's this coefficients and powers of x, so like a0, a1x, a2x squared, all the way up to an x to the n. Then all of the coefficients have to satisfy these equations. Yes, I have a better piece of chalk, but apparently I'm going to be disappointed. No, I'm going to go to my office and get some decent chalk. All the days does not have an umbrella. Okay. So I have these n plus 1 equations that have to be satisfied, but if I go ahead and write those out, I'd have a0 plus a1 x0 plus a2 x0 squared. So I'm just plugging in x0. An x naught to the n is equal to that corresponding y value. So I plug in x0 and I get y0. And I do the same for x1 and all the other x values all the way down to, oh, that should be a0. Yep. Xn plus a2 xn squared plus an xn to the n equals yn. Okay. Now, what we have is n plus 1 linear equations and n plus 1 unknowns, which are the coefficients. So everything matches up pretty nicely. But what I can also do is write out this system in matrix vector form. Write this way as V A is equal to Y, where A is the column vector of all the coefficients, and Y is the vector of all the Y values, and V is an n plus 1 by n plus 1 matrix. So the first column is going to be all 1s, because that's what was multiplying a0. And then the second column are all the x values. And then the third column is all the x values squared. All the way down to the last column, which is all the x values to the nth power. This is called a Vandermonde matrix. And although it's quite tedious, it is possible to come up with a formula for the determinant of this matrix, which I don't remember off the top of my head, unfortunately. But the point I want to make is that this matrix is known to be invertible if all of the x values, really if and only if, all of the x values are distinct, which we are assuming. So the coefficients, the a's, are uniquely determined. So that's one way to see that finding this polynomial of degree n has a unique solution. Now, there is another way to see that there's a unique solution, because suppose you have two polynomials of degree n that pass through these points. Then the difference of those polynomials has n plus 1 zeros, because they agree at those n plus 1 points. But if a polynomial of degree n has n plus 1 zeros, what does that mean? How many zeros can such a polynomial have normally? The degree n. But if it has too many zeros, the only way it can happen is if it's 0 everywhere. Yeah. So that's another way to see that interpolating polynomial is unique. Okay, so, but now that I've given a way of solving this problem, we can solve a system of linear equations, like by Gaussian elimination or whatever. I think, well, why are we even talking about this? What is there to do, really? Except there's a problem. So to answer the question, why not just solve this system, VA equals Y? There are two reasons. First, it's too slow. If you were to solve this system by ordinary means, like using Gaussian elimination or whatever, it would take on the order of n cubed, so number of arithmetic operations proportional to n cubed, and I use this abbreviation here, flops, which is short for floating point operations, so arithmetic operations, to solve this system. And what we will find when we look at other methods, it is possible to do it in order n squared. And that makes a huge difference when n is large. So solving a system like you normally would is wasteful. And the second reason is, and without getting too much into numerical linear algebra, because that really is a next semester thing, that if any of the x's are very close together, and the matrix V is said to be ill-conditioned. So linear systems that are ill-conditioned are very problematic for numerical work. So again, I don't want to get into this right here, but very sensitive to round-off error. Okay. So basically, you might not be able to trust the solution that you get. Now, that reminds me, since I said this is a next semester thing, the spring schedule is slow, I think almost finalized, because Dr. Schroeder put out a draft of it, and there may still be some tweaks, but so I can tell you that I will be teaching Math 610, numerical linear algebra. It will meet Tuesday, Thursday at 5:10 to 6:25. I wanted to have it at this time, but it conflicts with something else. Dang it. I know that some of you will be taking 773, and that is being taught by Dr. Chen, and here we go. The time will be Tuesday, Thursday, 1 to 2:15. Okay. Actually, does anyone have any other classes to ask about?
What about Dr. Perry's computer programming classes?
Right.
It's a 600 level, but I don't know the number.
It's like a 685, or it's like a topics class.
In this scheduled draft, I guess it's uncertainty about the time. It's tentatively put for Tuesday, Thursday, 11 to 12:15.
What about real analysis too?
Oh, right.
642 on the schedule too?
Yeah, okay. So 642 is Monday, Wednesday, 2 to 3:15, and 542 is Monday, Wednesday, at this time, 5 to 6:15, which is why I had 610 moved. So yes, Sophie, it's your fault.
Because I'm taking 610. Am I taking 7? I don't remember what I'm taking next week.
Probably. I know we talked about that, but yeah.
And I deleted it because I got a new phone. So.
Oh, right. Okay. Oh, well. Any other classes to ask about?
The 642 probably won't run if there's only 3 people, will it?
Iffy. Yeah, because
there's only 3 of us in 641 right now.
yeah. Because also there's talk about like cracking down on small classes, but if it could be argued that it's need for graduation, then I don't like the idea of saying like, oh well, we have a 600 level class, let's force everyone to take 610. Now, I love having more students, but I don't want anyone to just feel forced into it. So I'll find out. Okay. So we want to have so what I'm going to show you is a more efficient way of obtaining these coefficients, or some sort of coefficients for this polynomial, than just taking this relatively brain-dead approach. Even though in MATLAB it would be far easier to do this. Well, actually, no, because MATLAB has a function for doing polynomial interpolation. Because what I've done here is I've expressed the polynomial I'm looking for, this Pn of x, in the monomial basis, as a linear combination of the monomials 1, x, x squared, up to x to the n. If I were to express Pn of x using a different set of polynomials, then maybe I can get a simpler matrix to work with to make a system easy to solve. And in fact, what I'm going to do here is take that idea to an extreme and get the simplest matrix possible. And do what is called Lagrange interpolation. Okay. So Lagrange interpolation, I express Pn of x as a linear combination where the coefficients are just going to be the y values that I'm given. And I have these Lagrange polynomials that I'm combining instead of just the monomials. So the way the Lagrange polynomials are defined, each of these polynomials, when I plug in an x value, it must be equal to 1 if I equals j and 0 otherwise. Okay, so if I could come up with polynomials that satisfy all n plus 1 of these conditions, this for j equals 0 up to n, then I have my polynomial. So how can we do that? It'd be nice to have a formula for these. Well, first of all, what I've done here is I've specified what all the roots are. So I need these polynomials to be degree up to n. So here I have n plus 1 x values altogether. At n of them, it's supposed to be 0. So those are the roots. But if I know the roots, I have a factorization. So I can write this as a product of linear factors, x minus xi, for all I not equal to j. So that way, if I plug in any x equal to xi, where I is not equal to j, one of these linear factors is going to be 0, thus making the whole thing 0. Because this symbol means that I'm multiplying them rather than adding. But that will only help me satisfy this condition, that it's equal to 0 at all x's not equal to xj. What about making it equal to 1? Because if I plug in x equal to xj, then I get all these linear factors multiplied that are now non-zero, but the product of all of those isn't going to be 1. whatever I get here, when x equals xj, I have to make sure it's canceled out somehow. So I can just go ahead and do that. I'll divide by what I would get if x equals xj. And that gets the job done. So you can now confirm this condition. If I plug in x equal to xj, all of these will cancel out and give me 1. If I plug in any other x, one of these linear factors will vanish and make the whole thing 0. All right. So we can just go ahead and construct these for whatever data we're given and have our interpolated polynomial. And I'll show you with an example. So my data is, make a little table here. I'm going to have 4 points altogether. So numbered 0, 1, 2, and 3. My x values will be -1, 0, 1, and 2. They do not have to be equally spaced. I just picked them for this example. And then my y values are 3, -4, 5, and -6. Okay, so I have 4 points. So a polynomial I'm going to come up with is going to be a third degree, cubic. So I need 4 Lagrange polynomials in all. So my Lagrange polynomials will be of degree 3. So n equals 3. And my first polynomial, so I need to make sure that this polynomial, my first one, is equal to 1 if x is equal to x1, x2, or x3. No, wrong. When x is equal to x0. When x is equal to any of the other x values, x1, x2, x3, then it's equal to 0. So these are the roots. X minus x1, x minus x2, x minus x3. And then I can divide by the point where I want it to be equal to 1, x0 minus x1, x0 minus x2, x0 minus x3. Okay. That's what it would be in general, but now I can go ahead and fill in the x values I have. So that would be x minus 0, x minus 1, x minus 2, over minus 1 minus 0, minus 1 minus 1, minus 1 minus 2. Okay. And then if you were to take the time to simplify that, x cubed minus 3x squared plus 2x. Okay.
What is the -1/6? What do we divide by? What does that do for us? We divide by.
Well, that makes sure that if you plug in the first x value, x equal -1, you'd actually get 1. Because if I plug in x equal to -1, yeah, it causes this cancellation.
Oh, so just so that it equals 1, you do.
Yeah. Yeah, because the numerator alone is enough to make sure that these conditions are satisfied. I need to divide by something down to make that happen.
Okay.
Because the thing is, you want this Lagrange polynomial to have certain properties, like it equals something at certain points. And generally, you can't tell that at all by looking at this. Like when it's all simplified, it's like, well, but the factored form can help you see that. Well, I want to try here, if I were to move on to the second polynomial, So that must equal 1 at x1, the second point, and then 0 when x is equal to any of the other points. So what I'd like you guys to try is, can you get to this next step of writing it out at least in factored form, and just using like x0, x1, x2, etc., not the specific numbers. So how can I make sure that these conditions are satisfied? So similar to this.
X minus x naught, x times x minus x2 times x minus x2.
Yeah, so it's the way I always repeat to myself is it's x minus all the other points. Okay.
And now x1 minus x naught,
Yeah.
x1 minus x2, x1 minus x2.
Yeah. Okay. So, yeah. So you see the pattern. Yeah, because it's x1 minus all the other ones, and then you can fill in from there. Okay. Now, well, first, any questions about these first two? All right. Let's take it. Well, I don't want to switch boards yet. Now I'll take it a step further. Move on to the third polynomial, and this time I'm not going to write down these properties right here. But based on what we've seen from first two polynomials, can you jump directly to this form? Wait, I got to make sure I'm getting all of that on. Okay. All right. So what should I have here for the third one?
X minus x
Go ahead.
She's done.
Yeah, go ahead.
X minus x1 and x minus x3.
Yeah. Yeah. So you just skip x2, right? And
And then on the bottom you have x2 minus x0, x2 minus x1, x2 minus x3.
yeah, and because you're taking x2 minus all the other ones, you're never going to have division by 0. These will always be distinct. So yeah, and then if we were to do the fourth one, yeah, I think you guys get it. You do, right?
Yes.
Okay, good. Usually it's harder than this, so again, I'm pleasantly surprised. Okay. Okay.
Pretty sure we all learned this, right?
Well, not everybody, but
Oh.
well, yeah, maybe a majority, but not. Also, even then, it was like, well, a year ago or longer. So.
It was much harder the first time I saw it.
Yeah.
Okay.
It's like-
Yeah. Well, and then I guess you worked with some Lagrange in this, like in the summer.
Yeah.
Right. Yeah. So. Okay. So then, so once you have all of these, well, okay, I'll just summarize using the specific number. So I already wrote down the first one with the given data. Okay, so your interpolating polynomial P3, that should be y0, L3 0 of x, y1, L3 1, plus y2, L3 2. Because when we're constructing Lagrange polynomials, we only deal with the x values. We don't need the y values at all yet. Not until the very end. So I can fill in, okay, so 3 times that first Lagrange polynomial that I wrote down earlier. And then minus 4 times the second Lagrange polynomial, which would just be x plus 1, x minus 1, x minus 2. All right, and then the third y value is 5. So and in this case, the x value, this is at, okay, I'll just write it up here. This is x equals -1. This is for x1, which is equal to 0. This third term is for x2, which is equal to 1. And then for the last term, y value is -6. And we have x plus 1, x minus 1. So this corresponds to x3, which is equal to 2. Okay. And then it could all be expanded from there, which is kind of tedious. But the final result turns out to be -6x cubed plus 8x squared plus 7x minus 4, once it's all multiplied out. Okay. And then you can plug in any of the x values from a table and make sure that you have the expected y values. Okay. All right, questions about Lagrange interpolation? Now, in 560, I also cover Newton interpolation, but I'm not actually going to get into that here. We have too many other fish to fry. Okay. Now, in some cases, maybe constructing Pn of x just given these x and y values, maybe that's all the information you have. But another possibility is maybe the data is obtained from some known function, f of x. So the idea is f of x could be whatever function, and you're change of something that's known, and you're trying to approximate it by a polynomial simply because it's easier to work with, because you can differentiate or integrate it easily. That's actually going to be a running theme later in the semester where we approximate derivatives and integrals by approximating a function by a polynomial and then differentiating and integrating a polynomial exactly. So there's many situations where this kind of polynomial approximation is helpful. But then the question becomes, if we approximate f by some interpolating polynomial, so we go ahead and choose n plus 1 x values, plug them into a function and get the y's, and now we have a polynomial that hits f exactly at these n plus 1 points. But what about at other x? So if we know that Pn of x agrees exactly with f at the given x values, but we plug in some other x, just because it fits f exactly at those points, is it a good approximation of f at other points? We hope so. But we're going to find out that's not always true. We want to have some sort of formula that can tell us, that gives us some indication of what this error is. Now, so I have this proof that's actually can be found in the textbook, and it's a delightfully tricky proof of the error formula. It relies on some ideas from Calculus 1. So let's just define this rather strange function, phi of t. So it's equal to the error as a function of t. And then I have this expression where I have f of x minus Pn of x. But then I divide by, this is of x. Okay, where the pi is a polynomial that's just a product of all these linear factors, x minus x naught, x minus x1, all the way up to x minus xn. Now, unlike the Lagrange polynomials where we take all those linear factors except one, here we include all of them. So that's a polynomial degree n plus 1. Now, let's see. Okay. Now,
Excuse me, so we include all except one of them, right?
no, here we include all of them. Yeah, in the Lagrange polynomials we skipped one.
Okay, yes, you're right.
We're not skipping. Yeah. Okay, so. Okay. Now, first we're going to get some understanding of where this function phi of t is equal to 0. So if I plug in x equal to xi, so wherever you see t, t is equal to xi. What will I get? Keeping in mind that Pn of xi equals f of xi. So Pn is designed to match f at those points. Oh?
When you just have just ft?
Or f
No,
of t
well-
minus.
The first part
The
can't.
last
Zero.
part's gonna cancel.
Zero.
Yeah, everything's going to cancel.
Oh.
Yeah, because,
Oh, f of t is f of x. I.
yes,
Everything cancels.
yeah, so these agree at xi, so that's gone. And then here, this is going to be 0. Because I have, because what's going to happen is I'm going to plug in some x value here, and one of these linear factors will become 0, thus wiping out the whole thing. So this is going to be 0.
Wouldn't the top be 0 t?
Okay, think of x as like a fixed constant.
Oh, that's x is not t.
Yeah, yeah, t is your variable. Yeah, sorry, I should make it clear. T is your variable, x is some fixed constant. Okay. And actually that's very important for this next item. What if I set t equal to x?
Are you, do you
Well,
just
then
get for that, the numerator of the? No.
What?
You get 0.
Yes. Okay, well, okay, why do you get 0?
The pi is like those
Those
two,
cancel.
those two simplify, and then you get f of t minus f of t. And
Yeah,
then p,
yeah,
and then the
well,
polynomials.
Yeah,
That's my.
yeah, f of x minus p of x and x and x. Yeah, it's 0. And the other thing I should point out here, we're assuming that x is not equal to any of those. I mean, well, if it was, it would still be 0. But I'm in a case where x is distinct from all the other points. Because when x equals xi, we know what the error is. It's 0. We want to find out what happens away from that. Okay, so what this means is phi has at least n plus 1, n plus 2 distinct zeros. Okay. This is where I recall something from Calculus 1 that I'm hoping at least somebody in this room remembers.
How does n plus 2 come?
Well, we have n plus 1 of these points, and then this one. Okay. All right. Now, does anyone remember what Rolle's theorem from Calculus 1 is? Does anyone recall hearing of it?
Yes.
Okay. Can anyone tell me what it is?
Isn't it like that? It's related to the mean value theorem, I think.
It's used to prove a mean value theorem.
Yeah, okay, I knew it was related to
Yeah, I remember it.
Give us a hint.
Okay,
Without using the line.
I'll give you assumptions. Let's see if you, so. Okay, so if f is continuous, what's it going to be, and it's differentiable, I don't feel like writing out, the open interval AB, and f of A equals f of B.
Does it have something to do with the tangent line equaling something?
Yes.
Zero?
Yes.
Something about the tangent line, even, like, if that happens between them, there's something, 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 I don't know. C is a point?
Yeah, yeah. You're so helpful.
Okay, no, I totally got that before.
Yeah, so somewhere in between, well, actually, I can say open interval. So in other words, you know, if you have a situation like this, where the function values at A and B are equal, then whatever happens, like if it behaves like this, for instance, there has to be a horizontal tangent in there somewhere. There may be more than one, but the point is there is one. So here you have a function with, now these function values, they only have to be equal, they don't have to be 0. But if you have two equal values, the derivative has to be 0 in between. Now, let's try applying that to this situation. Here we have n plus 2 points where phi is equal to the same thing. In this case, it happens to be 0, which is not necessary, but it works. So, if phi has at least n plus 2 distinct zeros, phi prime has what? So,
Say that again.
okay, here we have agreement at 2 points that gives us a 0 of f prime. Here we have agreement at n plus 2 points. So what you can do is you can think of it as Rolle's theorem applied several times, like to each gap. So what can I say about zeros of phi prime?
How do you say that? Is equal 0? Is
At-
C?
Yes, but how many points?
N plus
N plus
1?
one.
Yes, because there are if I have n plus 2 points, there are n plus 1 gaps to put a 0. So it's like you're applying Rolle's theorem to each of these subintervals. So it has at least n plus 1, and all these subintervals are distinct. Okay. Now, I can keep going. So for instance, phi double prime would have at least n zeros and so forth. So how far can I keep going? Phi what? I want to get to a point where I have at least 1 0. But what derivative can I be sure has that property? N plus 1, because the order of derivative plus the number of zeros has to equal n plus 2. So I can keep increasing my derivative order and decreasing my number of zeros. So yeah, the n plus first derivative. So I know it has a zero somewhere. I'll call it an unknown point xc. And it lies somewhere among these x values, these xi's. That's all I know. But now I need to try to compute that n plus first derivative. Fortunately, it's easier to do than you might think. Okay, we'll make sure all of it's on video. Okay, so what?
So they can pause it.
Oh, good point. Yeah, well, I'll make sure I was out of the way a little bit. Okay. So, if we go back to our definition of phi, keeping in mind that Pn is polynomial degree n. Also, phi is a function of t only. T is your only variable. So you can think of x as being a constant. So, what would be the n plus first derivative of phi? Well, I'll start it off. F could be anything. We don't know anything about f. So that would just be the n plus first derivative of f. But then what? Yes, because Pn is of degree n. If we take too many derivatives, it's going to be 0. So that part's gone. Okay, and we only differentiate stuff that depends on t. Anything else is a constant.
So f of x is 0.
Well, but if it's a constant factor.
Oh, yeah, okay.
Yeah. So we still have to differentiate this, but this just sticks around as a constant. So we have f of x minus Pn of x over pi n plus 1 of x times whatever goes here. Now here we have a polynomial of degree n plus 1, and we're differentiating at n plus 1 times. Does anyone know what happens?
Just a constant.
It is a constant, but what's the constant?
Oh,
How
is
is
it
it
the
defined?
x? Oh wait, it would have to be x naught.
Well, one thing I can tell you is, regardless of what these x's are, this polynomial, I'll put it back up. This polynomial is called a Monic polynomial, because notice the coefficient of x in each of these factors is 1. So
Oh, it's gonna be n.
It's gonna be
warmer.
N plus 1.
It's just gonna be 1.
There's more to it than that. Now, yeah, the leading coefficient of this is going to be 1. So what I can say is pi n plus 1 of t is going to be equal to t to the n plus 1 plus lower degree terms. So if I take, because that's all you're doing, David, you're applying a power rule, but keep in mind you're applying a power rule n plus 1 times. So if I differentiate this a zillion times, or n plus 1,
So is it n plus 1 times n?
factorial, yeah. You're going to multiply all those exponents together, n plus 1, n, and so forth, all the way down to 1, so it's n plus 1 factorial. So that's what we have here, n plus 1 factorial. But now I know that this whole thing is equal to 0 at t equal to this unknown point c, or squiggly. So now what I can do is I can take this equation and solve it for this, because this is the error. So if I go ahead and set t equal to xc, if I rearrange this and I want to isolate f minus Pn, so what would that be equal to?
we just
y
be
t divided by, I multiplied by
pi n plus one.
And we substitute t equal to c, but okay, what do we have?
Divided by n plus 1 x squared.
Uh-huh.
We'll get times the pi n plus one.
Of x, yeah. Or actually, now I can write out what that is. That's how it's usually, so x minus x naught, x minus x1 up to x minus x naught. So this is the error formula. Now the point c is unknown, but if we could like come up with a bound for the n plus first derivative of f, we can at least come up with a bound for the error. So as expected, the error is equal to 0 whenever x is equal to any of the xi's, because f and pn are supposed to agree at those points, but not necessarily anywhere else. Okay, so this is the error in the interpolating polynomial, Pn. Okay. All right. Although if we had looked at the other form of interpolation, Newton-divided differences, we would have not have needed this tricky proof, but whatever. Okay. Now, I mean, this formula is all well and good, but we still want to have some idea, like, is it possible for this error to be large? And for that, I will point out a specific example where unfortunately it is. Okay. Now, I'm going to let my function be 1 over 1 plus x squared. And I'll look at that on the interval from -5 to 5. And I'm going to set my x values to just be the integers from -5 to 5. So I'm going to have 11 points altogether. So my interpolating polynomial is going to have degree 10. So if I were to graph f of x and, let's see. So at 0 it's equal to 1, and then it decays as we move away from the origin. So it's kind of a bell-shaped graph. It's nice and smooth. But now I'm going to fit a polynomial of degree 10 to this. And here's what happens. So first of all, I'm going to mark the x values. They're supposed to be equally spaced. Might not get it quite right in my drawing, but okay. So here's what happens when we construct this interpolating polynomial P10. Now it's going to agree with f of x at the points that I've circled, but what happens in between? So near x equals 0, it's actually pretty decent. But as we move away from 0, it gets ugly. In fact, in the notes, I have a plot in generated by MATLAB. Yeah, it pretty much looks like that. And in fact, reality is even worse when I've drawn the picture. So unfortunately, even just because the polynomial agrees with f at these equally spaced points, doesn't mean it's going to agree well in between. And actually, it shouldn't be all that surprising that it turned out this badly, because when you have a polynomial of higher degree, like degree 10, polynomials of higher degree have more roots. That means they tend to be more oscillatory. And sure enough, that's what happens here. But f of x is not oscillatory. F of x is smooth. So a smooth function like that is difficult to approximate accurately with a low degree polynomial. Now it's difficult, but not impossible. So the problem here is not just that we're using a large number of points to capture a smooth function. It's that they're equally spaced. So high degree interpolation, and as we can see here, it doesn't have to be all that high degree, with equally spaced points, your x values. Don't do it. It doesn't end well for you. This is actually this is a well-known example that any class in the subject should present. Does anyone happen to know what it's called or who it's named after? Yeah, Rungate. Yeah. So this is Rungate's example. We're going to see his name again. Toward the end, we'll get to differential equations and Runge-Kutta method. So it's him. Okay. All right. So this is a cautionary tale for high-degree polynomial interpolation. Fortunately, there is a way to improve the situation. Let's use what are called Chebyshev points. Or actually, I'll start with Chebyshev polynomials. Now these are extremely useful functions. We'll be seeing them more than once during the semester. They have all kinds of applications. So I'm going to define them as follows. So tk of x is equal to cosine of k inverse cosine of x, at least for x between -1 and 1. Now that doesn't look very polynomial-like, but you'll see why it is. So for instance, if I said k equals 0, what am I going to get?
Cosine k pi over 2.
But k is 0.
Oh, k. Sorry.
Yeah.
This is 0.
1. It's cosine of 0. Okay. What about t1? Yeah, because you have cosine of inverse cosine, those cancel, and you get x. Now, what about after that? You could use trig identities, which you probably all forgotten. Because I can use, I'm going to call this inverse cosine of x, I'm going to call that theta, an abbreviation. So cosine of k plus 1 theta, if I use a formula for cosine of a sum, so that'd be cosine k theta minus sine k theta sine theta. And then I could do the same thing with cosine k minus 1 theta. So that's going to be cosine k theta plus sine k theta sine theta. How many of you have forgotten these identities? Okay. Probably all of you.
Next semester of teacher.
Oh, okay.
So not helpful at all now.
Well, I know that Dr. Lee would say that there's only 3 trig identities you really need to know. Sine squared plus cosine squared equals 1. It's the only one that students ever remember. This identity and a similar one for sine of a sum. Because from those 3, you can pretty much derive all the other ones. So if I were to add these together, well, this is tk plus 1. And this is tk minus 1. So I have tk plus 1 of x plus tk minus 1 of x on the left side. These will cancel, so I'm adding these. And then cosine k theta, that's tk, because I use this abbreviation here. And cosine theta is just x. So I have theta equals inverse cosine of x, but that's the same as saying that cosine theta is x. So these two terms added together would give me 2x tk of x. So now I can go ahead and rearrange this. I can say that tk plus 1 of x is equal to 2x tk of x minus tk minus 1 of x. So this is called a 3-term recurrence relation. Each Chebyshev polynomial can be obtained from a previous 2. So we have a first 2, t0 is 1 and t1 is x. So I can say t2 of x is equal to 2x x minus 1. So it's 2x squared minus 1. If I want to do one more, t3 is equal to 2x squared minus 1 minus x. So that would give me, well, if you simplify this, what would you get? Yeah, 4x cubed minus 2x.
3 times recurrent, that just means that just because you're using tk minus 1, tk and tk plus 1.
Yeah.
So is tk minus considered to be a...
Oh, yeah, I forgot about him. Okay, yeah, minus 3x. Okay. Okay. Now, okay. Now, how does this help us with our error? Well, tk is defined to be a cosine. Well, how does cosine behave, like the values of cosine? Oscillate between what? Yeah. So we can say that the absolute value of tk of x is less than or equal to 1. Now I've only defined these on minus 1 to 1. Outside of minus 1 to 1, they can have a similar definition, but it's using hyperbolic cosine. But we're not going to get into that here. So the point is, they're bounded, because one of the problems with this error formula is you have this product of these linear factors, and that could get large. If we could try to control the size of these, that would help reduce our error. So that's why we're doing this. So what we can do is to exploit this property of Chebyshev polynomials, we can work with their roots. So once I choose a degree, I can let my x's be the roots. Let's see, I'll use not n, tn plus 1 of x. So I have x0, x1, x2, etc., up to xn. Now, I can compute those roots. So I have cosine of n plus 1 inverse cosine of x I must be equal to 0. But when is cosine equal to 0 generally? Pi over 2 and? Yeah, odd multiples of pi over 2. So I can say that n plus 1 inverse cosine of xi must be equal to 2I plus 1, some odd number, times pi over 2. So now I can rearrange this to solve for x of I. So xi is equal to cosine of 2i plus 1 over 2n plus 2 times pi. And this works for I equal to 0, 1, 2, up to n. So I can be sure that these are all distinct roots, and because they're cosine, they lie between minus 1 and 1, which is the interval I want them to fall into. So these are called the Chebyshev points. Now sometimes Chebyshev points refers to the roots, like I've done here. Other times they refer to the extreme, like the maximum and minimum, where you can use it working with sine instead of cosine. Now, what that means is each Chebyshev polynomial, like t plus 1 of x, I can write it in factored form. X minus x naught, x minus x1, all the way down to x minus xn, because these are the roots. Except I've forgotten one thing. If I multiply this out, what's the leading coefficient? The highest degree coefficient is what?
Coefficient would be what?
Yeah, because I have x to the n plus 1 time, and then other terms. But that's not the leading coefficient of a Chebyshev polynomial. If you look back over here, as I compute these, like t1, t2, t3, like here and here,
It's 2 to the minus 1.
yeah, it's the leading coefficient of tk is 2 to the k minus 1. Yeah, it keeps doubling because of a 2 here. So I'm missing a factor of 2 to the n. So whatever degree we have here, we have 2 to 1 degree less. And that's actually a good thing, because that tells me that the error formula, f minus Pn of x, which is my n plus first derivative over n plus 1 factorial times the product of all these linear factors. If I were to try to bound this, well, I still have this part here. That part's not going to change. N plus first derivative over n plus 1 factorial. But this part right here, what is that going to be less than or equal to then? Because the whole polynomial, all right, so this is less than or equal to 1 in absolute value. But I don't want the polynomial, I care about the product of these linear factors. So what is that bounded by? What?
X to the n.
No. All right, because Tn plus 1 we know is equal to this whole thing, but I only care about part of it. So what I can do is, knowing that this is less than or equal to 1, then the product of all these linear factors is bounded by what? 1 over 2 to the n. Yeah, so I can stick a 2 to the n in the denominator there. So that makes that denominator nice and big. Now, the n plus first derivative could still be big. So this does not guarantee that the error is going to be small. But it helps, because at least it prevents this part of the error formula from growing large. Now, this is for the interval minus 1 to 1. If you're working on a general interval AB, like in the Runge's example here, you have to scale it, but like b minus a over 2 to the n plus 1. But the point is, you can get a decent bound on how big the error can get. So So the Chebyshev points are, you think of as being kind of optimal. And now the thing is, what do the Chebyshev points look like? I can actually show you, I think we'll be out of time at that point, how they're distributed. Okay. Because the idea is, instead of being equally spaced along the, that's a semi-decent semicircle, instead of being equally spaced along the x-axis, they're equally spaced along the circle. So I'll pick out these, so I'm going to navigate around circle. Try to make subintervals of equal width. Okay. Except the intervals on the ends are smaller. They're half the size. But now, what happens when you take a cosine of a point on a circle? What? The cosine of a point on a circle gives you what? Okay. Sorry, a few phrases dropped, but I think for the most part the recording's intact. So cosine is the x value, because remember the formula for the roots, which is on the previous board, has the roots are equal to a cosine of something. So I'm just going to take these points and project them down to the x-axis. So it's just drawing vertical. And what you'll find is, as I get closer to the origin, the spacing between the points increases, and then the points get clustered as I approach the boundary. It's because of the slope of the circle. So these points right here, along the x-axis, these are my Chebyshev points. So you can see that distribution of making them cluster around the boundary helps with the accuracy of polynomial interpolants. And it definitely does a better job, not perfect, but a much better job with Runke's example anyway. Okay, I'm past time, but there you go. So we'll keep talking about interpolation on Wednesday and maybe calling on somebody, but not about this.